So let's have a look at the history of the Earth, one sample at a time. Here you can see a meteorite. This is a piece of rock from space that originated in the early solar system. This is probably more than 4.6 billion years old. Here's another sample that melted, a little bit more melting as it entered the atmosphere, but this is iron and nickel that formed when the solar system first came into being. This is the stuff that early Earth was made of. In fact, here's a piece cut away from one of those meteorites, and this is iron and nickel compounds, crystals that only form in zero gravity in space. This is what would be composing the center of the Earth, the inner core, the solid core. This one's very interesting though. This is some olivine minerals inside of that iron nickel matrix. This is the piece of a mantle of an ancient planet or small asteroid or large asteroid that exploded and sent fragments into space, eventually to rain down on Earth. And these fragments would have come down to Earth any time in the last few thousand years. So if we fast forward to about 3.5 to 2.5 billion years ago, Archean life form had begun, cyanobacteria followed, and the cyanobacteria started to create oxygen from the carbon dioxide and methane in the air. But most of that oxygen was consumed in early Earth to precipitate the iron that was contained in the early oceans. Here you can see these banded iron formations that date back over 2.5 billion years. A little bit of Northern Ontario history. Here we have what's called a breccia. This is actually an impact breccia formed by a catastrophic asteroid impact in the Sudbury area of Northern Ontario. The ground was ruptured over 100 kilometers or so, and these pieces of granite are older than that impact, and they were thrown up into the mix, and then this darker material, this mafic material, surrounded this and created a rock sometime after this collision. Many places in Ontario or Canada, you'll find rocks like this. They're often mistaken for granites. They're not. They may or may not have been granites in the past, but these are rocks that have been buried very, very deep and have been distorted and sheared and compressed to form these bands of felsic material, silica-rich, iron-rich, and mafic material, magnesium-rich. And these 1.6 billion-year-old gneissic samples are from Middle Ontario, I suppose, around Algonquin Park. One of the rocks north of Kingston that underlie the limestone I talked about in the last lecture is syenite. It's like a granite that many of you are familiar with, but it's missing the mineral quartz. These are intrusions that would have come up through the surrounding rocks about 1.1 billion years ago. So from about 2.5 billion years ago to about 650 million years ago, there was a very slow evolution of single-celled life forms, primitive multi-cell life forms, cells with nuclei, and then finally around slightly older than 600 million years ago, up to about 550 million years ago, these cells coalesced into complex life forms. Here you can see a large sea frond that would have been anchored to the floor of the ocean 600 million years ago, obviously made up of many, many cells with some distinct functions. 600 million years ago, that's the Ediacaran. But it wasn't until the Cambrian period, about 500 million years ago, plus or minus a few tens of millions of years, where life became extremely complex and gave rise to creatures like this incredible trilobite fossil. You can see the detail, the outer armor. You can even see the eyeballs. It had teeth. It had articulating exoskeleton. It could move. Came in different sizes, along with many other similar organisms and other organisms that we don't see today. And all of this was happening 500 million years ago, but at the same time as these sand ripples were deposited on a beach somewhere and preserved by burial, and then eventually turned into rock, the Cambrian. In my last video, I talked about Ordovician limestones, and here are some Ordovician fossils. These are what today we would call scallops. These would have been on the seafloor 460 million years ago. And there's fragments of these on the steps of Miller Hall and some of the other buildings on campus, as I noted in the previous video. We see some very spectacular evolution of what I suppose today we would call squid. These are belemnites that are about 380 million years old, progressing through history in a period of time called the Carboniferous. This is where most of the Earth's coal was formed, and the Earth was covered in very, very thick fossils. Here's just a small little fossil example of a fern leaf, a tree leaf, that would have been deposited 300 million years ago. And these leaves would have come down into this Carboniferous mudstone. You can see there's another layer, a different leaf, and been preserved as sediments continuously stacked on top and eventually turned into rock. Here we are into a period of time called the Jurassic. This is midway through the age of the dinosaurs, although the dinosaurs were not the only game in town. Here you can see some beautiful preserved ammonite shell fossils. These look like they would have been created by a jeweler yesterday, but they're in fact 150 million years old. And the shells themselves have been replaced by various minerals to create this hard fossil that can be enjoyed today. Most of the major dinosaurs we associate with Jurassic Park, the movie, are actually from the Cretaceous, including this little raptor-like dinosaur who left a footprint in this mudstone, possibly in a tidal flat, 100 million years ago. Moving on through history, these are some shark teeth. Sharks have been around for hundreds of millions of years, but these are fossilized remains of shark teeth from about 50 million years ago, and they actually look very similar to shark teeth of today. However, at some point about 20 million years or so, sharks got very big. A megalodon shark tooth. And these are monsters of the deep that lasted for about 10, 15 million years or so. And then the shark returned back to the size that we see it today. Here we have some petrified wood. And if you're curious and you've been wandering around any parts of the world, you may find some wood-like samples that are very much rock. And the cellulose in the cells gets replaced mostly by silica and turns it into these beautiful remnants you think you could throw into a campfire today, but they're very much rock. And these can be anywhere from 100 million to a few million years old, depending on where you get them. So skipping through a very large age of mammals, simply because I don't happen to have any mammal fossils in my house, just go to a few thousand years ago, which is a blink in geological time. Here's some lava that was created during the explosion of Santorini Island in Greece. This is very much rounded, telling us that this piece of lava has been rolling around on a beach, getting worn down into this beautiful shape for a few thousand years. And then I just want to end with a few samples collected recently. These are samples from a particular volcano in Iceland, and these rocks formed in 1984. I was just entering university when this molten rock turned into rock to be found today. And in places like Hawaii and Iceland and other volcanic areas, you can pick up rocks that are days old. They're still going to be pretty warm to the touch. So 4.6 billion years, a few decades. Geological time.